My name is Elena Sokova. I'm the Executive Director of the Vienna Center for Disarmament and Non-Proliferation. And it's my pleasure to welcome all of you here in the room who joined us in person in Vienna, and others who are joining us online, still filing in as far as I can tell. Today we were going to focus on quantum technology and nuclear security. I know in everyday news we hear about artificial intelligence, but this is another big technology that makes more and more both into the news, but also in the portfolios and concerns of many of the professionals working in a variety of security areas. And nuclear industry, nuclear facilities, technologies is not something that is staying outside of this realm as well. Today we'll try to first focus a little bit on the technology itself and try to understand it, what it can do, and or these multiple quantum technologies can do. What that might mean for nuclear security, as security of nuclear facilities and materials. We'll try to separate hype from some of the real opportunities and concerns that come with any kind of new technologies that are being introduced. And we will learn probably quite a bit from this very established group of experts who definitely know more than most of us about both the technology but also nuclear security and the intersection, potential implications of it. So hopefully we'll have a much more clear and grounded picture after today's seminar. And I'm looking forward to the discussion myself, but my role is very limited. And I have Dr. Sarah Case Lackner, who is a senior fellow here at the VCDNP, will moderate the discussion and make sure that we stay on track with it. Sarah, please.
Thank you, Elena. And thank you, everybody who's come here today, those of you watching online, those of you here in the room. We have a lot of people. I think that's great because honestly, I have been looking forward to this discussion since I came up with the idea in conversation with two of our panelists a few months ago. So I'm excited that you get to see what came out of that. And I'm going to tell you a bit about the conversation that we're going to have today. We have four fantastic panelists. So I think you're very lucky to get to hear about this from them today. I want to start, I'm going to do this in alphabetical order, Mr. Rodney Busquim y Silva. He brings over 25 years of experience in the nuclear sector to his job at the IAEA, where he is the head of the Information Management Section in the Division of Nuclear Security. His responsibilities include overseeing the information and computer security program there. So that's fantastic. He will have a lot to say about this. And then Hannes Hübel. He is at the Austrian Institute of Technology, and since 2015, he has led the experimental quantum key distribution development at AIT. So then we also have, and he's head of the competence unit, Optical Quantum Technologies at AIT. Now, we also have Kevin Lee from the Canadian Nuclear Safety Commission. He currently heads the CNSC's team analyzing disruptive, innovative, and emerging technologies. And this team aims to ready CNSC to evaluate and regulate these technologies in the nuclear industry. So that gets to really the point of regulating it. And last, alphabetically, is Emma Wong, who leads nuclear innovation and quantum technologies at the Electric Power Research Institute, where she works on advancing new nuclear technologies and connecting industry, regulators, and global partners. So this is a panel you get to talk to today. I'm going to be asking them some very interesting questions, I hope. for about the next 50 minutes. And then we're going to turn to all of you. First, we'll do a Q&A in the room where you will be able to pose questions to the speaker. And then we'll turn to our online participants. I'll talk more about that when we're done with this conversation, but for now, let's get started. And I actually really want to start with what are quantum technologies? I think that for many of us in this room who are not, I mean, I'm a physicist. That doesn't mean I have any idea what this is. So I think for many of us, we don't really know what it is. So let me start with, Hannes, we often hear that quantum technologies will be the next big thing. I hear it at least. But that seems to cover an awful lot of different things, say a basket filled with different objects. Could you explain in layman's terms, what are the main technologies that everyone is now referring to in the news and everywhere as quantum?
Okay, thank you for inviting me, Sarah, and thank you for your question. Let me start with quickly telling you how important quantum physics is for all of us, and that you're using it already nowadays. If you think about it, I mean, quantum physics is the best theory of nature that we have currently, but it's not only that. It basically gave us also great innovations like the microchip and the laser. And without those two pillars, our current communication technology, information technology society would not be here. And definitely the audience online would not be able to listen to this exciting talk. Apart from that, it gets even better, because now we are really able, for the first time in human history, to manipulate single atoms, electrons of matter and energy, photons. And with this capability, suddenly arise new opportunities, new applications, which are much more powerful than classical ones. And in this so-called second quantum revolution, we have basically three large application areas. The first one, you probably all heard about it, it's quantum computing. So a quantum computer, which is basically using this quantum resource, those individual atoms, they can basically calculate all possible paths, all possible computations at the same time. So you get a tremendous speed up in the calculation. And with this, you can, for example, use it for much faster optimization, because all the routes are calculated simultaneously. You can basically use that for solving logistical problems. You can also use a quantum computer to simulate quantum systems. So if you want to develop new medicine, new pharmaceutical products, or new materials, you can basically much better understand and model the physics that we can do nowadays with classical computers. So they are really very large application areas and very important ones for a quantum computer. Then the second field is quantum sensor, quantum measurement devices. So in a quantum computer, if you want to build it, you want to really shield it as much as possible from the environment, because everything which comes in, be it now some light, vibrations, or whatever, will basically disturb this very delicate computation. So you basically shield your quantum system as much as possible. In quantum, if you use a quantum sensor, you do the opposite. You want that the quantum system starts to interact with the environment, because it's so sensitive, then it can really measure minute changes in the environment. For example, electromagnetic fields, the gravitational field of the Earth, and that again gives you new applications. For example, you can use it for very accurate inertial sensors, so you can basically navigate without a GPS signal, or you could think, okay, you can make a very accurate map of the magnetic field of the Earth. It's slightly varying, it's not constant. And if you have this map and you have a very precise sensor, again, you can basically measure, okay, when I move along, how does the field vary? And then again, then I can find my position with it. There's also a lot of medical applications for it too. So again, it's a very large field of applications. And the third one, and that's where the AIT and my group specializes in, is quantum communications. And there the focus is on security, because again, quantum systems have special characterizations, like for example, that you cannot make an exact copy of a quantum system. So if I give you a quantum system, you cannot clone it, you cannot copy it, which we all can do classically. So it's very hard to basically double information or steal information if you use quantum communication. And this is the field, as I said, we are specializing in, and will also counteract some of the attacks that are possible by quantum computers. But I think we'll come to that in a minute or so.
Oh, thank you. You were actually shorter than
Oh,
planned.
okay.
Yeah, no, but I think we'll have plenty more time then for questions, which is fantastic. This was a great introduction. That was really interesting. But then my question is, okay, what are some concrete examples of what this means? And maybe we could apply it to the nuclear sector. Emma, would you be able to give us some introduction into what these quantum technologies mean for the nuclear sector?
Yeah, sure. Thanks, Sarah, and thanks for the introduction and invitation to be here today, and for everyone who's here and online participating, because this is, I think, a quite important topic to realize that these technologies are here today, and some of them will be here tomorrow, right? So as Hannes just talked about, quantum sensing 1.0 is already here today. It's a laser. It's your MRI machine. It's the NMR machine that you use in some of the labs. You don't realize it, but you have quantum sensors around you everywhere already today. What was really interesting, and like now how we're like really manipulating these quantum properties, is what we call quantum sensing, well, I call them anyway, quantum sensing 2.0, when we're actually using these more quantum properties to do more. And we're actually seeing a lot of these sensors being developed. They're being employed in a lot of different applications. But when you come to nuclear power, a lot of people say, nuclear power, we don't innovate. Why would we innovate? It's working today. But we have a lot of problems and a lot of things that we would like to be able to do that we've never been able to sense before. For instance, we have a lot of buried infrastructure. It would be great to be able to understand what that buried infrastructure, what's happening to it. It's probably been buried for 40 plus years. However, if you dig it up, you might actually damage that infrastructure when nothing's actually happening to it. So you've caused an issue. So a lot of the things that we're looking at is how do we actually look at what's actually happening in places we've never been able to sense before. So these are a lot of the areas that we're looking at, is looking at what couldn't you do before. If you look at electromagnetics, if you look at even just magnetic fields, and you think about where could you employ that? You have a lot of motors out there that you need to take offline to actually do a test to see how it's functioning. But turning something on and off when it should just be constantly running is not actually a healthy thing for equipment to do. So for equipment reliability, if you have a better sensor to understand the equipment health, that is a huge advantage. But where are these things being used today? I mean, a lot of things can be used well, let's just say we're using a lot of these in different industries right now, and we would love to be able to employ them in the nuclear industry. But right now, a lot of it is an engineering problem, and it's a trust problem. Can we trust these to be implemented inside, the protected area? I would say let's start outside first, maybe near intakes, near land that's outside, and then start moving in once we build more trust. You've also talked about, quantum networking, quantum communications. EPRI has done some work on this area with some electricity utilities already. None of them have actually been implementing this quite yet because there's a lot of infrastructure that needs to be built out for that. And then to understand what some of those vulnerabilities still might be or what changes you might have to do if you're going to employ some of these new technologies. And then for quantum computing, the quantum computers out there, don't have that as many qubits as we might want to do for a full optimization. However, there's quantum simulation. You have also, quantum algorithms that could do some predictive analytics for you if you were going to do some AI applications. A lot of these are being developed today. So I would say for the newest version of quantum that's coming out here, that's truly manipulated, there's a little bit of time and consideration before it's fully implemented to where we can answer maybe some of these questions that you may have.
Can I ask a follow-up question
Sure.
with just 1 minute? So what kind of timelines are we talking about? Happening tomorrow, happening?
I would say for quantum sensors, they're already here today. So they could be implemented with the correct engineering in the next few years. That is not an issue. I think some people may have heard of these things called atomic clocks that could be used for synchronization. Those exist today. However, their price point for what we would want them to do in the energy industry, that price point is way too high for implementation. So there's probably some manufacturing supply chain improvements that could have before they're widely implemented. But say if we had infinite money, we would install these things for synchronization today. So it's not, is the technology ready? Is the rest of the whole supply chain, the engineering, the trust factor, are those ready? Quantum networking, same thing. It's not that they don't exist. We've seen them being tried out. Even, I was talking to Hannes about it, Vienna even has a test case with multiple nodes that's being used, but it's probably going to come down to a trust factor. Do you trust this? And then how expensive is that infrastructure going to be to build out? And then for quantum computing or quantum algorithms, that quantum advantage, it's actually finding those use cases that you would want to apply this to. You can have these algorithms today, but I would say that the amount of parameters that you have in a lot of these problems are still too many for it to be used to its full advantage. However, a reimagining of what that problem looks like to bring down the parameters might actually get you where you need to go. So a lot of these smart people today, a lot of that focus will bring down a lot of those time points. So to answer your question, quantum sensors are here today, so I think practical application, 2 to 3 years. Mm-hmm. I would say quantum computers, more quantum advantage, I would say it's more near term, but more like maybe 7 to 10. Just because of where we are in its thinking for the energy industry. Mm-hmm. I will say some of the other industries that need this more quickly, they'll bring that into reality faster.
Okay, so that leads really naturally into the next question I have, at least. Okay, so this is coming really fast, and then I'm going to turn to the nuclear regulator on our panel. I know you think about this from the Canadian perspective, but since your focus is really on how do you regulate, how do you manage the challenges of innovative technologies, Kevin, what are the challenges that this is going to pose for nuclear regulation? And what are you thinking about in terms of quantum technologies at this point?
Okay, so I'll tell a bit of story first. We have this perception that innovation is like new, it's been happening lately, and it's really accelerating, and it is. But CNSC, Canadian Nuclear Safety Commission, has been around since 1946. And in reality, it's been regulating innovation for 80 years. What has changed a lot is, again, this perception that things are happening far quicker. And without question, they are. An interesting kind of segue is last week we reviewed at the CNSC our conduct for technical assessment of innovative technologies. By and large, we're looking at SMRs. And we were looking at, okay, how would a subject matter expert assess, evaluate, and make a recommendation on a given SMR technology? And we found that by and large, what you're looking at with SMRs isn't that indistinguishable from what we traditionally have or what we had in the 50s. So it's almost back to the future. What's changing, though, particularly with AI, and specifically we've been looking at the last few years, is what we traditionally do when it comes to conduct of technical assessment to make that evaluation. Is it applicable when you layer something with AI? And we've kind of come to the conclusion that yes, there is a distinction and that we need to be very clear about how we articulate that distinction. I would say if you look at some of the work that we've been doing internationally, particularly with the US NRC, UK ONR, and the trilateral paper we put out 2 years ago, it was sort of the first kind of foray into regulators putting some form of statement out there. So it was really just general considerations. So right now I would say all regulators are kind of grappling with that AI question. And I think the lessons we learn as we grapple with that, we work internationally, we work domestically with our industry, with our academia, we will come up with, I think, a new methodology of how to address uncertainty and how, with that uncertainty, you foster safe operation. Now, the question always will become, well, you don't want to have it so that you have so much defense in depth because of that uncertainty that it's not economically viable for anyone to actually implement. So if we kind of look ahead and what we might be thinking about when it comes to quantum, I think, Dr. Hübel, you nailed it at the start. And my view on quantum and where it's really going to come and be very effective is with fusion technology. And that's something we're also readying ourselves for. So if you're looking at fusion technology, you're looking at, and this is, in my mind, fusion is the true innovation within nuclear. It's changing from one paradigm to another. And the reason you are not going to achieve that will, in essence, be ameliorated by quantum technology, in my mind. Because number one, how do you maintain your criticality? How do you maintain and make sure that the flux, quantum computing will assist in that? How do you do the materials, the new materials that will be needed to withstand temperature? Quantum can do that. How are you going to, in essence, draw the heat off and actually make it commercially viable? I believe quantum's going to do that. So if you kind of look at the end state and where I see the biggest sort of emphasis around quantum, it's not necessarily, although it will greatly assist current and future fission plants, it's more the way they're going to enable fusion plants. So from my mind, the next big hurdle will be international regulators, domestic regulators getting together, understanding quantum and understanding the implications that will have down the road on what I think the true future for nuclear is, which is fusion.
That brings a really new angle to this, which I could see a lot of nodding here. So I think that we'll see if we can pick up that thread perhaps a bit later. Before we get to that, I actually want to turn to the IAEA though, and continue this discussion on how do you manage new technologies, and ask Rodney, I don't know how much the IAEA has thought about this, to some extent at least. Can you share some of that thinking about how the IAEA is approaching quantum technologies and their potential applications in the nuclear sector?
Sure, Sarah. First of all, thank you very much for the invitation, opportunity to present what the IAEA has been doing. As we know, the IAEA is a science, technology-based organization, and it serves as the focal point for nuclear technology. There are many different ways that we have been supporting member states. For example, in the Division of Nuclear Security, we develop guidance, we publish technical reports, and that cover innovations, that cover what the nuclear sector needs in terms of nuclear security. We also coordinate research projects, and this is an activity that the IAEA has been conducting that has quantum technology element, a few that we have been running since 2019. They touch on the use of quantum technology. Sensors, that was said, development of materials for monitoring, and we also have information sharing activities. We will have a conference, CyberCon, from 10 to 15 of May, and there are a few papers that talk about quantum technology for cyber security. And we do have a conduct training course. So in terms of quantum, there are a lot of opportunities that we see, specifically when it deals with simulation. One example that Kevin just gave us, it's about fusion. And I also believe that's it's where we have the next step in terms of innovation in the nuclear industry. And for sure, quantum computing will make it possible from all the angles, from materials to simulation, to how we're going to maintain criticality, how we're going to operate the reactors. Also, there are opportunities in terms of simulating different scenarios for safety and security. This is something that we have been looking into. Of course, there are a lot of, in terms of material development. That's another topic that the IAEA has been looking into. And in terms of nuclear security, post-quantum cryptography, how we're going to manage the data that we have available today that an adversary can have access and in the future can hack using quantum computing. So, and communication, security communication. We are looking into this, and it's very positive that we have this conversation today because in the last 1 or 2 months we have been discussing the start of another coordinated research project on quantum computing focus on security, specifically on cybersecurity and communication security, and that will allow us to be up to date with what's said by our colleague, that it's a matter of not a decade, but a few years when you see this technology being used by all of us. So we have been thinking and finding the best way to support member states using the tools and activities that we have at the IAEA. Thank you.
Thank you, Rodney. And what I was really happy, you brought up some of these security angles, and I'd really like to get into that more. Because that's what we came here today really to talk about, is security and quantum and nuclear. And so to get into that a bit more, I've got more questions, because I always have more questions. Let me turn back to Hannes, because you haven't talked since the beginning. If a non-state actor, possibly even a state-sponsored actor, was to acquire quantum sensing or computing technologies, could this enable new types of attacks? And how likely is it that these non-state actors could get these capabilities? And what kind of timelines would we be talking about?
So we heard just before some of the pros from our quantum computer, so basically devising new materials which are basically more resistant or basically use it to optimize certain processes. But there's unfortunately also a darker side to quantum computing, and this ties in with information technology. And just to maybe go a step back, how does our standard encryption nowadays work? Yeah, so if you do some shopping on the internet, or I want to maybe exchange a secret message with Sarah, how would we do or start with this? So the first step is the so-called asymmetric cryptography. So first we would need to exchange an initial secret, and that initial secret is normally in the form of a digital key. Yeah? So I would, for example, have this key and somehow have to transmit it to Sarah, and for that we basically use some asymmetric cryptography. So those are special algorithms which have been devised, which are very hard to break for classical computers, and we can basically exchange, or can exchange this key to Sarah. So now we both have the same key, and now it's quite straightforward. We can then basically, for example, Sarah writes her message, she uses this key to encrypt the message, sends the encrypted message to me, so nobody can eavesdrop because it's encrypted. I have the same key, and the same as if you have a key and a lock, I can just use this key and unencrypt the message or the cipher diagram, and then I basically have the message back. And this second step is called symmetric cryptography, and that's pretty much safe, even against attacks of a quantum computer. But this first step, so this asymmetric cryptography, really relies on mathematical hard problems, yeah? So the security of this first step of basically exchanging the key, exchanging the secret with Sarah really relies that it's very hard for classical computers to basically do these calculations, yeah? It's not impossible, but it would take thousands or billions of years, depending on how long this secret is, yeah? So up to now, it has been pretty safe to basically use this type of cryptographic primitives. But now comes the quantum computer, yeah? And there's a special algorithm called Shor's algorithm, and it has been proven that with this algorithm you can basically exponentially faster decode or crack this asymmetric cryptography than it's possible with a classical computer. So we're not talking about thousands or millions of years, but we're talking about hours, yeah? So the last studies which came out showed that if you have a reasonable sized quantum computer, maybe 10,000 qubits, fairly, I mean, they can be still have error rates of 0.1%, but it's proven that with this you take about 8 hours to basically crack this secret key. And this is a real danger. And the danger is not only when it will happen, I come to that, that's the second part of the question, but what an adversary can do now is the so-called harvest now, decrypt later attacks. So even if they don't have a quantum computer yet, yeah, and Sarah and me have maybe a secret that we want to keep safe for longer or for a couple of years' time, somebody could basically just grab this encrypted message and basically wait until they have a powerful quantum computer and then decrypt it, yeah? And then they have again the secret again, yeah? So it depends really how long you want to have your secret be in the private domain as well. And this ties now in with when do we have such a power? When would an adversary have the capability of cracking it? It's of course a very hard question to answer, but if you ask the experts in the field and if you look, okay, the tremendous progress quantum computing has made in the last decade. I mean, we started in 2010, you had maybe quantum computers with 3, 4, maybe 5 qubits. Now I think the latest have a few thousands already, yeah? So it's been really, really a steep increase, and I think most experts would say that within 10, 15 years there will be a powerful enough quantum computer on the table, yeah? Maybe even faster. I think Emma believes it's faster, and I agree with her, because this is really, you know, predictions that we have on current technology, on the current progress, but you don't know what's happening. I mean, this is a vast field which has been largely unexplored. People can work on the hardware, make improvements. People can make it basically less error prone. They can work on quantum algorithms as well, which might give a speed up. So I think this 15 years is probably more on the conservative side, and I believe, or Emma believes as well, it might be much, much faster. So we really have to act now, yeah, if you want to make some changes, and it takes years if you basically want to completely change your cryptographic infrastructure in the various institutions or companies. Yeah, so really you have to think about what we can do now to counter this threat. And one of the possibility is, again, coming from quantum key distributions, or QKD, which basically allows you to exchange this initial secret without being vulnerable against attacks either from classical or from quantum computers. So we call that information theoretic security. So you can give whatever power you want to the adversary is still not able to basically crack this key exchange. Yeah? And once you have this key exchange, you can do your symmetric encryption, which is also secure against quantum computing attacks, and then you are safe. And this is really taken serious. Yeah. So this is why there is for an initiative now by the European Union, the so-called EuroQCI, European Quantum Communication Infrastructure, which has the aim by about 2029 to have a European-wide quantum communication network employing QKD in order to secure governmental data transfer. And it's based on a fiber network on the ground, but there will also be a quantum satellite to basically link cities that are much further apart, for example, in Western and Eastern Europe. So it's really something that everybody considers a threat, that we don't know when it's coming, but it will come for sure, and people and institutions have to prepare for it.
Well, so that was exactly the change in tone and the kind of things we wanted to hear about. That was, but Emma, I want to take it further. Can you? Yeah, further. Let's keep going. Building on what Hannes just described, all of these concerns, can you talk a little bit about the implications for the nuclear sector, and particularly if quantum technologies are deployed in IT or OT systems, are there some new vulnerabilities that we should be worrying about, thinking about at least?
Well, I would say if you're implementing anything new in your IT and OT, there's always something new to think about, right? And so having said that, if we're talking old nuclear, like anything that's already existing, it's been running for probably 40 to 60 years, your OT systems are very, very old. They are probably, you know, from the 70s per se, or even like older than that. And when you think about that, if you are implementing new technologies onto them, there's a huge integration piece that has to go with that. That in itself is a vulnerability, because these old technologies, those people who made them originally probably do not, I don't want to say don't exist, because some of them still exist, but a lot of those people who developed them, the theories behind them, they're retired, or they may have passed on to whatever. And so integrating something brand new is going to take a whole new way of thinking, because you have to, why did we do this to begin with this way? And then when you integrate this new technology into it, whether it be a new sensor package with the new communications package attached to it, to then maybe an edge computer that then communicates to a quantum computer, all of these things stacked together is a whole new way of thinking. And so it's those new connections, the new integrations, that I think will be the vulnerabilities that we need to really examine. The sensor itself is going to do what it does, but like when you transfer that information from what it's actually sensing, the algorithm it needs to look at, to actually decode what does this really mean, like how do we make sure that that algorithm is going to actually be safe, right? Well, we do that today, but a lot of that, has some other, sensors around it or things like that, so you can actually cross-verify what you're looking at. And then when you communicate that, you say it's a communication network that's now quantum, it's all entangled, but what does that mean? If it's a physical connection, do you have to do now, what is that physical security that now you have to rebuild it? Because now we're talking about everything's cyber secure, we have all these things looking around, but if it's now a physical connection that you actually have to safeguard against, what does that mean if we're taking all of our guards out of the power plants? We're trying to reduce all of these physical aspects. What does that mean? Or if you're communicating between things and it's it's going across fibers or however, but it's now that physical connection because it's all entangled that's actually important, that's different than the way we think about it today. So it may actually introduce new things you have to think about. And then a computer, it's a computer. It's going to sit wherever it is, but then you have to think about, okay, do we have to make sure, it has the cooling aspects it may need if that's the methodology you're using, if it's actually safeguarded against other things. So that's all of that to think about as well. And so that's both the IT and the OT. And then the communication between the two will be hugely important.
No, thank you. So now we have a lot more things to worry about. We're just adding them on. So now I'm going to turn to the side of the table that is thinking about how to make sure that those bad things don't come to pass. And I know, Kevin, the job of a regulator is to do your best to ensure that the right kinds of measures are in place for safety and security in the nuclear sector, whether we're talking about these quantum technologies or normal threats. When you're thinking about this from a regulatory perspective, is there anything in what we just talked about with quantum that is going to make it a bit different from the other technologies that you're thinking about when you're thinking about regulation, if we're focused very, very tightly on security?
Mm-hmm. So the nice thing is, if you take a look at, for instance, AI, we have a wealth of standards on how to safely implement AI. And we don't, of course. You cannot necessarily at this juncture qualify an AI system. We're working towards that. So what you're looking at, let's say right now with AI, is I think a learning platform from a security point of view as to how you might regulate quantum down the road. And I think one of the things that's kind of changing a bit is that nuclear is now joining with other high interest industries, other industries that are highly regulated. And I know in Canada with our CSA group, we're starting to look at a standard that would go across all high interest, highly regulated industries, including nuclear, for what does good look like? How do you implement in a manner that's going to protect the plant and make sure that from a security point of view, you're safe as well. So we're starting to see that happen. Now, part of the issue with doing these endeavors is you don't have the human resources that you necessarily need to do that. And I think quantum, as you were saying, there's not a lot of people looking at it right now, that by and large, individuals within the nuclear community who are looking at quantum, and then let alone those that understand it, because I certainly do not fully understand it. I don't think anyone does. Emma might, but that would be the exception. You're going to be hard pressed to start thinking now about what that might look like. How do you do those protections that need to be in place? And I think quantum is we're going to have to learn the lessons from AI and try to implement them in quantum, but it's a different animal and it's a different way of operating. AI and quantum don't, in my opinion, share a lot of similarities in terms of how they safeguard and how the security measures can be put in place. So it's going to take a different way of thinking. It's going to take more individuals who are in that, let's say, the quantum community, coming over into nuclear and helping us move that bar forward. And, Emma, your predictions as to when it might be implemented, let's say. Sensors, I agree totally here at this point. Quantum computing, the jury's out. You know, you're 7 to 8, you're probably looking more 15 years. But the question then becomes, okay, well, that's what we're thinking now. But how conservative is that? And you know, is your 7 and 8 right, or is it more like 2 or 3? Because if you look back about 5 years ago, no one would have thought AI would be where it is now. So I would argue that one of the biggest things, challenges we're going to have is that the innovation around quantum will be far quicker than most people believe. But that remains to be seen. So again, human resources, the willingness to work with other partners, and needing to bring in, let's say, individuals from the quantum realm. And we need to get, let's say, our heads around AI as well. So there's a lot of different things coming at us. You're looking at new technologies around SMRs, you're looking at new technology around AI, and then you're looking at quantum and, let's say, fusion as well. So there's a lot happening, a lot quicker than it ever has in the past. So I would say that's kind of where we're at. Limited resources, a lot happening.
Yeah. And it's a sobering observation, particularly because every time we turn around and look at AI, it seems to be moving faster and faster, and new capabilities are coming out. So what is that going to mean for this technology as well? Before we start having that kind of discussion, though, I want to ask Rodney one last question, which is so when you were talking previously, you talked about some cooperative research projects that are already underway about quantum. What else? Basically, could you just elaborate a bit about what the IAEA is doing right now on quantum and nuclear security?
Thank you. Yes, I can for sure. I appreciate all the panelists that have provided a lot of insights why quantum is and will become more important for nuclear security. And if you look from the cybersecurity point of view, and we live in an age where data is really important for all of us, and communication, how we transmit information, it's really important. So there are a lot of considerations that was said about harvest now, decrypt later. We have decades of data on how to operate nuclear power plants that's used for plant performance. And there are nuclear power plants who are using AI, as Kevin told, to predict if you need or not to have maintenance of a certain pump or piece of equipment it's failing or not. If you think that we didn't touch this that much, we could actually think on the possibilities of using quantum computing to train large language models and to make the current way you are doing this more efficient. That will have a consequence in terms of saving energy, saving resources in the future, but what that means for all the information that we are planning or using for improving or the way we operate nuclear power plants. There are other considerations was said about OT and how the legacy systems that we have in nuclear facilities. There are considerations in possibilities of using quantum computing to develop faster, more complex malwares. That's something that we see now with the use of AI, and there is a limitation in terms of the capacity of building this, but what's going to happen in the future if you have more computational capacity. So those are few of the considerations. How does it work at the IAEA? We prepare a project that's a proposal for a coordinated research project that's then open to all member states all over the world to present their proposal. And to be able to start this project, we need to have our questions well defined. What type of research questions would you like to have answered, and how the whole community can get together and help us to make sure that we are ready and prepared, because as was said before, 7, 15 years, it doesn't matter. We need to be prepared right now. We cannot just react, we have to act now. And that's what we're doing in terms of AI, and that's our plan in terms of research and capacity building for what comes next in terms of quantum computing.
Thank you, Rodney. So we are very lucky. So we are ahead of schedule a little bit. And so because of that, what I'm going to do is I want to actually ask a bonus question before I turn to the audience for your questions, because I think that you've got these great people up here, and I want to ask them one more thing. And it's going to be the same question for all of you. And what I want to know from each of you, and we'll start back with Hannes again, is what is something that this discussion we've had today has missed that you think our audience here in this room and our audience online needs to make sure that they take away from the discussion?
Okay, so maybe one thing we have not spoken is also a bit quantum communication. It's also a kind of double-edged sword, yeah? Because we were saying, okay, you can use it to secure communication, yeah, but that applies also for the other party, your adversary, yeah. Mm-hmm. So especially Emma was mentioning, okay, once we have this wonderful entanglement spreading a world which is also known as the quantum internet, maybe people can say quantum information network, where you basically just exchange quantum information, yeah. And as I said before in the intro, it's impossible to make exact copies of this quantum information, yeah. That means everybody who has access to this network can, again, use it to distribute completely secret messages. There's no way of a lawful interception. There are no more points of lawful interception like we have nowadays in our communication rooms, etc. So surveillance, spying in on other parties will be much, much harder, yeah? So either you have to then say, okay, those quantum information networks are somehow government, state-owned, and you restrict the access. You can maybe restrict the technology that you need to build it. But then, you know, we have also the possibility to have those quantum networks via satellites, and that is very hard to basically restrict that, because, I mean, a lot of nations can now launch satellite at least into low Earth orbit, and then basically can communicate securely over this. So this is really something to think about. How important, or what would you do basically if you cannot have access to the information, or if this surveillance on parties is no longer possible? So I would just say, so I mean, with quantum communication, you really, or quantum technologies overall, you always have to basically think from both standpoints, yeah? So what does it do for me, but what can it also do for the others, and how basically can I do I have to deal with it or not, yeah?
And that's going to be a challenge for, sounds like, law enforcement and government.
Exactly, yeah. It's quite big. I mean, at the moment, the technology is expensive, is maybe hard to engineer, but this will change probably in the future quite a lot. Maybe also with the help of AI, who knows? You know, they basically, maybe that helps us also to make it cheaper, faster. Yeah, it's really, it's an exciting time we are living in, but yeah, you don't know where it's going, so people have really to prepare for it.
And with that, Emma, what have we missed? What have we not talked about yet?
I don't want to add more doom and gloom.
That's what we're here for.
However, one thing I do want to maybe, well, I'm going to add something positive in the movie, something negative right after that. But the innovations that I think that will come with quantum technology is just because, you know, you're going to be able to have very sensitive sensors that can sense almost anything. Well, not almost anything, but like you can get almost real information. A lot of measurements today are done kind of around about, this is what we think it is. Even like a temperature sensor is really sensing something else to tell you temperature. Well, you can use a quantum sensor to actually get a real gauge on what the real temperature is to a really nice significant digit to do really accurate modeling. But when you think about that, that's where you start thinking about, now you can do real-time predictive analytics, you could do real-time prediction and monitoring, lots of trending. This is where it now leads into like real-time operations, which leads to automation, which leads to a lot of things where you could be like, well, oh, you have a fully automated, truly automated, in real-time power plant. You could say you could do some of it today. Yeah, you could, but like this will actually give you a lot of information that could fully automate something. Now, and then on the flip side of that, if you think about like, okay, if that's where we're heading, because A, we don't have the workforce is kind of becoming smaller and smaller, just because we don't have the physical amount of people. That's why we're like, how do we use AI? How do we augment our workforce? How do we do as much as we can with what we have? Everything is driving towards like a future where automation is, or at least semi-automation is a real thing. And then you have to really start thinking about those vulnerabilities that you have attached to that as well. whether or not you are actually using quantum technologies with that. But quantum technologies, while could be an adversary, also could help you in those areas. So I think from both sides, as you said, it could help you, and it also is, on the flip side, can also hurt you.
Okay, so we have a positive and negative. Now, the other side, Kevin, what have you got?
So you've both kind of skirted around, which is what the thing I think we're all missing and continue to struggle with when it comes to AI, and that's the human factor. With AI, I know that in most meetings that you always kind of have to bring people back to the human aspect of it, the human factor. The AI technology, for many people, is almost a means to an end of itself. And they forget about the fact that it has to be sort of a partnership. So Vivek Agarwal from INL, I think he coined the term HAT, a human AI team. And that's a good vision to have, but I fear that as much as we're almost kind of paying little attention or giving short shrift to, let's say, the human acceptance of AI, the human ability to trust AI, and the human ability to actually want to work with AI, means that you end up focusing too much on the technology and not enough about what does it do for the human, how does it enable the human, how does it make the human better, more efficient, more productive, more whatever. And I worry that with quantum, we're almost, from a lot of the discussions I'm involved in, we're going more and more down that sort of just the technology and not enough about the human interaction with the technology and how humans will, you know, if they have issues right now with AI, with quantum, it's probably going to be exacerbated. So I would say getting a handle around the interaction between the two, the human and the technology, is probably the one thing we're not talking enough, in my opinion.
And I like that everything comes back to automation. And when it comes back to automation, it comes back to quantum, but also AI, and we have to deal with the fallout of that. Rodney, I'm sorry you got the last slot there, so.
Always the last, okay. No, I appreciate what was said here about everything. What I think that's missing, and I agree, is in terms of the agency always looks on sharing information, that we need to have the mechanisms to provide information, capacity building activities that will allow the nuclear sector to understand the use of quantum computing or quantum technology and to understand the benefits. Because when we hear about new technology, we hear a lot about the benefits, and then when it comes to decision making, it's all about the risks. So we need to be able to clearly communicate what are the benefits and what are the risks behind any technology. And quantum computing is not different. Automation has been around for a while, decades, and have been using. There are boundaries, as was said before. The difference is we have faster automation, we have AI playing a big role in terms of how we do run SMRs, so microreactors, in remote locations without any intervention from humans, or we will not do this. So I think the conversation about capacity building activities, and I'm talking about workshops, trainings that are here now, and then we'll make sure that the human factor, the human resource that you have in the future to deal and to work with this new technology, quantum technology, we will understand what are the benefits and what are the risks of using it.
Okay. So thank you, Rodney. Thank you, everybody, for this. But now we have the next part of this discussion. What I'd like to do is get out to all of you in the audience. Those of you watching online can't see that we have a very full room here. And perhaps there are some questions, but I am also going to send, before we turn to these questions here in the room, I want to warn our online participants, start thinking about some good questions, put them in the Q&A, and we'll get to a round of online questions as soon as we take in a couple of questions from the room. Is there anyone here who has? Okay, so we have one here and one here and one here. So, oh, there's four. So let's take the first two, and then we'll take the next two after that.
Good afternoon, everyone. I'm Pushkar Chaparwal, Managing Director of Parin Consulting GmbH, based here in Vienna. First of all, thank you to the panelists for this very interesting and very relevant topic. My question is actually quite straightforward. I wanted to ask, considering the pros and cons and the security threats which quantum computing and quantum technology also brings, along with the pros, do you think there is a need for a regulatory body or international body, let's say what the IAEA is for nuclear energy? Do you think there has to be sort of an organization which should regulate and control the information? Thank you.
Okay.
Can I jump on that one first?
Can we get the second question, and then Kevin, this is, I think we had the gentleman here in the front. Okay. Then please, we just want to get two of them, and then we'll get the next two.
Okay.
Thank you. Can you hear me?
Yes.
So Rodney, I have a question for you from IAEA perspective. What are the biggest challenges in preserving trust and integrity? So those are the two elements that came up during, I think, Emma's presentation as well. In preserving trust and integrity in data as systems become more digital and increasingly automated, and related to that, how does IAEA think about the use of data, of its data in judicial proceedings? Thank you. International proceedings. Thank you.
So, why don't we start then with Kevin, and then we'll go to you, Rodney, and then we can ask for more comments from there.
Okay, so the simple answer to your question is absolutely. However, the issue around that is that I first started hearing talk about we need an international body to oversee AI the same as we have an international body for nuclear, i.e. the IAEA. And there should be such a forum, there should be such a body. It doesn't seem to have legs right now, there doesn't seem to be the will, but I firmly believe that such an organization would be a very valuable asset. The best we can do right now is utilize something like the UN or the IAEA to sort of, at least within our playing field, have that forum and that ability to have that international body that's overlooking it, at least in the nuclear industry. But in terms of AI writ large, well, that's not happening. Doesn't give me a lot of hope for it happening with quantum, therefore.
So Rodney, would you like to take on that?
Yeah, I agree with Kevin. I think under the one house approach, what the IAEA is doing for AI is looking how AI can be used and in the future being regulated for the nuclear sector. And always from the perspective that's a new technology that brings a lot of advantage and has a lot of risks. And as you probably know, the way we're looking at it, and it'll be the same for quantum mechanics, quantum computing, is that humans are always in control, what means the final decision of any action relies on a person to decide what will be the next. And what I can say is that my personal opinion, I agree that we should have a way to do it. And IAEA, at least for AI right now, is doing a great job trying to bring together all the member states under the same umbrella how to use AI for nuclear technology, not only nuclear facilities, but other facilities that work with great sources and use digital systems that may or may not employ AI. And if I understood your question regarding trust integrity, under the IAEA, we do have different departments and divisions that deal with the use of data. Of course, we do it internally as an organization, a big organization, how has security means to maintain member states' data, and I can tell that's it's highly secured, and we are providing support to member states in explain and teach them and provide guidance in how they should apply the mechanism to also maintain the trust of the data, I think.
Okay. Emma, Hannes?
I would like to tackle the regulatory question, unless I'm misunderstanding the word regulator. So I used to work for the U.S. regulator in nuclear power. So in my opinion, I do not think there should be like a U.S. regulator on quantum technologies. I see it more like maybe a standard organization on like how, for instance, it's technology. So like how should a sensor, if you want to use it, what attributes should it have, what protections it might need to have in the integrations and things like that. I mean, we don't have a regulatory body for like high-powered computing, for instance, right? Yep. So why would you want one for quantum computing, but maybe there are standards and best practices that you might be able to use for that. So regulatory bodies, as I see it, is probably not the way I would go with that. More standards and maybe consensus building about what it should look like instead.
I agree.
Yeah, I might follow this up to your question as well. I think you're doing a terrific job here at the IAEA to basically keep the kind of nuclear genie or the lid on the nuclear genie, because I think it's really important that not too many people get their hands on those kinds of technologies. But I think it's much harder with quantum technology, because it's not something. Even with AI, we always see it with social media how hard it is to regulate that. Yeah. And quantum technology is really something you can maybe in the future really build in your own secret research laboratory. So with very little exposure to the outside world. So as long as you don't say, okay, I have now a quantum computer, and you basically invite people to basically use it, so maybe via some kind of online connection. If you just use it for yourself, there's nearly no way of basically prohibiting this. But what I think Emma said is good. You could still basically put some standards in, or at least for then corporations which basically maybe sell that to an end user, those computers, that maybe for certain application there is a limiter in there, or some kind of prohibitor. But otherwise, I think just to basically regulate the technology itself, I think it will be very hard to do.
Okay. So I'm going to turn back to the audience. We had another 2 questions. One here and the gentleman here, and then on this side as well.
Thanks. I'm Harvey Zoden. I was a lawyer in the Carter administration. So as a lawyer, I don't understand the technical aspects of what you're talking about. And that goes to my question. First of all, I'm very happy that you talked about AI and quantum computing in the same discussion, because both are things the public doesn't understand. And at least for AI, which I know a little bit more about, even the experts don't know quite how it works. So how can you start to make decisions about both AI and quantum computing? And if in a democracy or any form of government actually, you need an informed public, how are you going to bring the public up to speed in order to make these existential decisions, no matter what the regulatory model is or whatever? And I think with AI that a lot of people talk about a lot, there's still not a lot of knowledge about that. Quantum computing in some ways seems easier, but in other ways seems difficult. So can you talk about that? Thanks very much.
Let's get the second question.
Yeah.
Thank you.
Getting that. I'm sorry.
You're very eager. We like that.
Thank you so much. My name is Ali. I'm with the League of Arab States. Thank you, Elena, for having us here today. And thank you for the panelists for the valuable insights. And thank you, Sarah, for being an excellent moderator. My question is, what is the role of the private sector in developing quantum technologies, and how reliable would be a technology that is being the private sector is involved in to be used in the nuclear field?
Okay, I think we have some good and very different questions. Kevin, you seem very eager to start, so we're going to start with you, and then...
Yeah, I'm going to jump on the first one, and maybe to clarify a misconception I might have placed in people's minds on the first one. I don't think any nuclear regulator in the world is looking to regulate AI. What they're doing is they're viewing AI as a tool that will be used in nuclear activities that are regulated. So it's just a different type of tool, and you're looking at that tool and how it will be deployed and how will it be deployed safely. But you're not going to, as a nuclear regulator, ever regulate AI. So in my mind, it falls to state actors to set up the preconditions, and in various jurisdictions that's being done. Generally speaking, except I think for maybe the EU, when it comes to AI at least, you're not getting very granular into what does it look like to deploy something that's going to be safe. It's mostly about, make sure you don't discriminate using an AI, don't make sure, so that's where, let's say, nations are going right now. But I think it's incumbent upon them to start saying what good looks like within AI. How do you deploy it so it is safe? And that's why one of the things we're moving towards, as I said, is kind of partnering with other industries that are going through the same thing so that we set up a common understanding that you can then communicate to the public and saying, yes, AI is being utilized in our case with the limited ability we have within the nuclear realm. Here's why we're deploying it. Here's why we think it's safe. And for instance, what will happen in Canada, let's say, is the first time you have an application or an amendment to a license where a nuclear operator of a power plant is looking to deploy AI in a safety significant system, that's going to be a public hearing. So that's an avenue for Canadian Nuclear Safety Commission, for example, in a public forum to have the proponent come forward saying, here's why we're going to do it. I alluded to conduct of technical assessment, how our staff will say, yes, we've made the judgment that this will be a safe deployment. Here's our reasons why. So it's limited in terms of what a nuclear regulator can do to kind of build that public acceptance. I think it falls more on the shoulders of national, international bodies and governments to do that. And the same thing I would suggest applies to quantum down the road.
So I'm going to then turn to
Yeah, maybe
Hannes.
I would like to follow up your question. It also a bit ties in, okay, what you can use. Yeah. And so if we really want to deploy quantum technologies, and I'm speaking now specifically about quantum communication, because this is quite advanced. I mean, we have more or less commercial products, which we did test it out here in Vienna with some of the federal agencies in Austria, but of course we would like to go also on the utility market with it. For utility companies, what you really need is certification. Yeah, so this is really the word to look for. Yeah, and this means that basically some recognized public authority gives you the rubber stamp on your device, saying, okay, you adhere to a certain sets of standard, and the box does exactly what it says on the outside. Yeah. And this is a quite long, drawn-out process. I mean, for most of our cryptographic equipment, it's already there, so if there's modification, they can modify it, but for quantum technology, since it's a newcomer of the field, you basically have to run through this whole chain, and it basically starts with setting standards. So basically, people first in standardization organizations have to agree, okay, what is quantum communication? QKD define it really, okay, what parts does it consist of? Then you can basically look at those individual parts and set standards, then set maybe some testing methodology. So how does each part has to be tested in order to verify it does it adheres to the standard or it adheres to the protocol? Then you can put it all together, put it into some kind of testing laboratory, and then, as I said, you need at the end of the day some kind of national authority or maybe a supranational authority, which basically gives you a certification stamp, which says, okay, to the buyer, then to the customer, even if it comes from a private company, okay, this product is certified to do key exchange via quantum cryptographic means and is therefore secure against a quantum computer attack. And I guess, I don't know, because I'm not an expert in certification, we're doing this now for quantum com. I guess it will also be for quantum computer or quantum sensors in future. Because otherwise it's really hard for private companies, like you said, to basically bring their products on the market and have basically government customers from the government, because they will not touch it. And even if you go to banks, to the financial sectors, because they will also say, okay, because in order, again, you probably trace back to regulations where it says somewhere in the regulation, okay, this product has to be certified to this and this standard in order to be used in your corporation. So this is, I think, a very important, and the EU is really pushing that, because we see it's a hurdle, because although we have the technology is there, is commercialized, it's not accepted yet by the customer. And although even if they wanted it, they are legally not allowed to basically employ it, because it has not the certification stamp yet.
It's really helpful. Emma, do you have anything to add to that?
I do, if we have time.
We have lots of time.
Oh, we have lots of time. Okay, so I'm going to have I'm going to build on what you just said. Yeah, certification and standards are good, but I think your larger question, what is the role of the private sector? It's huge. Startups are the private sector. Private investments are the private sector. The utilities, a lot of them are private, some are state-owned, but these are a lot of people who are driving that innovation. They need something. They need to solve a question. They need to operate longer. They need to build in extra capacity. They need to do a lot of different, they need the grid to stay on. They are the drivers, and they are also the value propositions for the business return on why you would even do these innovations to begin with, why you would even implement them to begin with. So the private sector does have a huge role into this, because if not, you would not see these innovations move. If you just relied on public, the governments, to do all of this, yeah, that's great and all, but would they drive it as hard as what companies need to survive or to innovate to or to bring it to that next step? So I'm seeing lots of startups in these areas, in all of these different quantum technologies, and they have new IP coming through all the time that is maybe the next jump, the next step that gets implemented into a wider system. But your next question was like, how is it going to be reliable to use in nuclear, right? Well, there's a nuclear regulator who will then test and ask for, they're going to have a list of questions. They're going to have to really think about what they're going to ask in order to let this be implemented inside the protected area if it's for safety. There's a lot of areas that are non-safety that could be used. You could use anything you want, right? You could paint it whatever you want, to be honest. But I'm going to use one example of when even in the public sector, so in the United States, trisofuel was developed at a national lab, very public, right? The regulator still had to go through all of the steps to say that it was still okay to be used. So even though it was done in the public sector, doesn't mean that it's still okay and safe to be used inside nuclear power. So regulators, it doesn't matter where it's coming from. To say that it is reliable to be used is at their purview if it has something to do with safety. Now, I will say on the flip side, if you're going to use it in any other parts of the plant, utilities, they're in the business of providing power. They have a public mandate. In the end of the day, they need to stay on. They also need to return some sort of money so they can do maintenance and all of these different things. Because they need to stay on, they're also going to do their due diligence to make sure that this isn't something that's returning bad information and all of these other things that are not on the safety side. So they also have their own reasons why they want to make sure that these are also to the highest standard possible to be used in these facilities. So either way, if it's the utilities looking at the technology, because they question a lot, believe me. I almost think sometimes they question more than the regulators do, but the regulators ask different questions than they would, right? Because it's true. And then the regulator asks lots of different questions that we also have to think about on the safety side. So for me, the role of the private sector sometimes is a public partnership, public-private partnership. Sometimes it's the public sector driving it. Sometimes it's the public sector driving it. But either way, it still comes down to kind of the regulator to say yes or no on that.
Yeah, but you've made a valid point in the fact that within nuclear, basic IAEA premise is that the operator has primary responsibility for safety. So you are correct. They do have a clear line of vision on safety, and it's in their best interest to do so.
And if you can just add, from the IA point of view, nuclear security is the responsibility of the state.
Yeah.
So I agree 100%, first with his Kevin comments about the first question, but also regarding private sector. I think the private sector, it drives us with the use of innovation, and of course, it's the regulator who would say is reliable or not. And the goal of the IAEA, as I said at the beginning, it's a science and technology-based organization that from where we can find all of us guidance. We publish a lot of technical reports based on research that we conducted together from member states, where we have the private sector have national labs, we have different organizations, the academia, all together that allow us to, through the information sharing activities, bring to the table what are the advantages and disadvantages of using a certain technology. And right now, what you're doing in terms of quantum computing is specifically thinking on how we can actually improve the way we communicate the advantage and the risks behind this technology.
Thanks to all of you. I want to thank you to those of you in the room who posed great questions. But let's turn to our online participants. Maybe we can take 2 questions, and then we'll see if there's anything in the room before we take any more.
Wonderful, thank you. We received a couple of questions online. One very interested in the fusion quantum nexus and how that could play out. This is a pretty specific question, but I'll read it off for those who can comment on that. And that is, the understanding is that current supercomputers restrict the number of superparticles we can simulate, which limits our understanding of complex plasma dynamics. So is the thought that future quantum advantage primarily would allow us to scale up particle numbers directly, or will it introduce new optimization algorithms that require fewer parameters to achieve high resolution results in our pursuit of fusion? So a very technical question, but I thought of interest, and maybe some of those on the panel can comment. The other one is more specific to nuclear, and that is, will legacy security controls still be effective in the quantum era, or do we have to rethink this entirely for current nuclear power plants?
Oh, those are some good questions, both highly, deeply technical and very security-oriented. Hannes, do you want to start?
Maybe I start. I take the first one, a try at least. I think both will happen. So on one hand, on the simulation side, so especially I think as Kevin was saying, on the material side, you really basically want to understand much more the material properties, yeah? And for that, you basically use the quantum computer to really simulate the alloy that you have in material, so the interaction between the atoms, the molecules. So this could be either by describing better the interaction potentials, Hamiltonians now, so really going into the deep material physics, also the number maybe of atoms. But I think the number of atoms is probably not so relevant there. So this is the first part. And I think for the second one, for the optimization now, how you basically put your magnetic fields, how you put your sensors and so on, this I think you can do on a much higher level where you might need less parameters, or even if you need the same amount of parameters, you basically get to a better optimization, and you maybe keep the plasma much more away from the wall. So again, you have basically less heating there and things like this. So, but I think maybe Kevin has a bit more understanding of the fusion process than I do.
You've actually explained it very well, and I totally agree.
Thank you. And I hope I answered the question as well.
So, Emma, do you have anything to add on either of those that you'd like to bring in there?
No, I agree with you, but like until we have a lot of these I guess computers or hybrid computing systems available, then you'll really see what the limitations are. Or maybe there are not as many limitations. But that is a huge discussion point, and actually this year there's going to be a lot of those forums that are going to start discussing this. What does that nexus look like? I've actually also seen some of these algorithms being put together for this and being run. So this is something a lot of people are really thinking about, but to see where the true limitations are, I think it's going to be based on the technologies.
So, Rodney, can I maybe turn to you, especially for that second question on security systems?
Okay, can you repeat the
Mark,
question?
could you reread it for us?
I was focused on the first one.
Yeah, the first one, it was very detailed, very technical. But the second one is, will current legacy security controls still be effective in the quantum era, or do we have to rethink this?
That's a good question. I think you are rethinking right now. We're rethinking in terms of cryptography, how we're going to manage cryptography when you have quantum computers available. I think there are some questions about what we call the IAEA DCSA, Defense and Computer Security Architecture, and how we deploy defense in-depth and graded approach on the cyber side. So, and as I said, in terms of quantum communication, and if we continue to discuss in the deployment of advanced reactors, considering remote operation, remote or operation from distance. Those are considerations in terms of, I'm not saying that they don't apply, I'm just saying that the cybersecurity controls and measures, we have to rethink and maybe change the way we are doing, because quantum computing will change the way we think about some of the cybersecurity considerations. One of them is cryptography.
Kevin, do you have anything to add on either of them before we?
No, I'm good.
Okay, then we have a few minutes left. We could take one more question from the audience. If there aren't any, I think we'll move into our closing. Oh, but we do have one. There we are.
Good afternoon, everyone. I'm Antonio Di Buono from UKNNL, National Nuclear Laboratory. I have a question. Which are the nuclear-specific requirements that are likely to be resolved externally, and we need more focus within the nuclear sector?
Okay. So for that, who would like to start that one? I think you're talking about human resource requirements. Kevin?
I'm going to hold on that one.
Am I?
Okay.
Can you repeat the
Actually,
question?
Yeah, Antonio,
yeah,
could
there's a way. Okay, yeah, if you
Could you repeat again?
I just want to make sure I understand where you're coming from.
Yeah, because most of the technology has been developed outside the nuclear sector. So which are the requirements that within the nuclear we must address for deployment in nuclear? So I'm imagining harsh environment deployment,
Okay.
radiation detection, this kind of.
Oh, okay. That's a bit different than what I
Yeah.
thought. Okay.
I can start and then they can.
Okay.
Okay.
Okay, so now that I understand the question, sorry, I thought you were addressing something completely different, but extreme environments are something that I'm specifically looking into, because that's a lot of the environments that our current classical sensors do not do well in, or they fail at a periodicity where you have to keep replacing them. So you don't want to have to keep replacing different sensors, either due to radiation, heat, or pressure, right? Those are the big areas that you'll want to look at. In addition, sensors are always having to be recalibrated, classical ones. When you have a quantum sensor, if you're going to put one in, because they're based on atomic quantum properties, the sensor itself is basically drift free. Now the accompanying electronics and things like that, those are also have drift properties, but you can get closer to a drift free measurement. And due to the frequency that you always have to calibrate a sensor, this is like highly looked at as something that could be very, very important in certain areas, especially like for temperature. If you're looking at, you need a temperature sensor just in a room for fire watch to determine if you're heating up too much and there's a fire, especially like historically we've had events at power plants where a fire has propagated in like the cable tray room. Not a great day, but if you need sensors in there to determine what is going on if you don't have cameras inside those areas. So even cameras, the lenses themselves degrade when you are in extreme environments as well. And so to your answer, all the extreme environments are of extreme interest. Especially if you are going to go into a higher radiation area just to do temporary sensing. Those are also needed because you're always doing some sort of maintenance work or inspections, because you want to look at all these different materials in highly irradiated areas. So those would be the most important areas. Now, are we going to go and do those first? Probably not. That creates a lot of testing. If you can imagine, if you're going to put a tool or a sensor in there, you want to be sure that it's going to be highly reliable. It's going to give you the right information. The whole systems package is actually engineered for that application. That's a lot of work and testing, especially since I know there's a regulator who's going to ask me a million questions about why is this ready to go into that area. I totally understand why you ask those questions, so we're going to test for those conditions to ensure the sensor is still reliable to what it's rated towards, right? That's where standards come into play. The rest of the package, because it's not just the quantum part, it's the whole package that has to also be rated to what it needs to be doing. And then the information that comes off of it, same thing. And so hopefully that answers your question, but you can always test those in other areas first before you move into the highly extreme environment areas.
Any brief addendum to that before we
Yeah,
go to our closing?
No, I'd say that Emma's absolutely right, and then if you look at, let's say, the activities of maintenance in high radiation field, refurbishment, or decommissioning, when you are able to match a drone or robotic system with, let's say, an AI sensor, your lifespan within that environment for that tool is greatly enhanced. So, yeah, you got it.
Can I just thank you, Antonio, for the question. I would say from the cybersecurity point of view, when you think about the information, the data that we are dealing with and how we will be dealing with safety and safety-related systems in a nuclear power plant, this is a consideration that we have to bring from the external world to the nuclear sector.
So,
maybe just
Yeah.
very quickly, briefly. So I'm not an expert on nuclear power plants, but I think what's important is exactly that those questions or those discussions take place, yeah, and they take place basically with the people who are the experts on the nuclear side and the experts on the quantum technology side, because we work in our labs, we understand the quantum part, but we don't know all the possible application and use cases, and therefore I think it's very important. It's just such a cross-cutting technology that we really need to engage basically with the end users, with the customers, to really see, okay, what are the challenges they are currently facing, and really can we help or not. Yeah, I think this is why it's really nice to be here, to have maybe this kick-off, start maybe in-depth discussion in the future.
and I hope we'll keep having this discussion exactly for that reason, that it's good to just be having conversations between different sectors, different technology experts, between regulators, policymakers, diplomats, all of you here in the room. And with that, we're about to close, but I always have one last request for my panels, which they never like, but I do it anyway. And this time I'm going to start with you, Rodney. And that is, in one sentence, can you just give a pithy statement that it would be useful for everybody to walk away with from this event? What do you think they should take home?
Okay, and I like when I ask these questions because you never know what to say and then you ask anyway. From my point of view, I'm just kidding. I think quantum computing or technology, it's reality, it's here, and we need to lay the right foundation. We talked about regulation, we talked about public opinion, human factors, cyber, and all the physics behind the quantum. So we need to do it. We need to do it right now, today, so it will enable progress and not trigger uncertainties how we apply in the nuclear industry.
Super. Thank you, Rodney. I appreciate your helping us with this. Kevin, you're next.
So I'll try to do it in one sentence. And that's with both AI and quantum computing. Technology is not the end user, humans are.
Oh, I like that one.
Perfect.
That's a good one. Emma, now you have to top that. You do not. That was not true.
God. Okay, no, but the one thing I would like people to take away is that quantum technologies is a broad term, and quantum computing is not. Quantum communications is not quantum sensing.
Yes.
They are all very different, and they all have different readiness levels. And technology readiness level is not the same as deployment readiness level, especially in nuclear. So that is a key thing. In addition, it's going to come down to a lot of engineering and communications. It may not come down to the actual technologies themselves. So, yeah.
That's a really good point. And Hannes, for our last comment.
Last comment, so I would say maybe if you ask me one sentence, I would say securing our nuclear future with quantum technologies. I think this is really a way forward, and I'm not thinking always about securing in terms of cybersecurity, information security, but I really like what Kevin said, really trying to use that for our next generation of energy supply, which is definitely fusion, which I think will be a huge step for humanity if we achieve that. And whatever quantum technologies can help to do that, I'm all for it and go for it.
Well, then I would like to close by thanking our speakers and everybody for being here today with us. So please. A great discussion, and we are now finished right on time, so thank you all for that too. And I wish you all a great afternoon. Elena, do you have anything further?
No, yes, I'm really blown away by the discussion, and very pertinent and interesting insights that you guys provided. I think the next one should be on quantum and fusion.
I think so too. That's what it sounds like.
But anyway, thank you all. That was a fascinating discussion.